Now that we have a good understanding of work, let's talk about heat, which is energy transfer through random thermal motions. Let's think back to paths 1 and 2 that we looked at in the last video. Both paths we've examined connect the same initial and final states. They're both Athens to Atlanta or Atlanta to Athens, right? And we've seen that the works W1 and W2 are different because the areas under these two curves are different. But internal energy is a state function, so delta U must be the same for both paths. So the confusing thing here is, where does the extra work go if not into a change in internal energy, delta U? Delta U is the sum of work and something else. That something else is where the extra work goes, quote unquote. What accounts for the balance of the energy change? Well, heat, of course. To segue from work to heat, we can imagine that work is the non-random coordinated motion of particles within a system, while heat is the random motion of particles within a system. And we can apply energy to random or non-random motions. Changes in energy are equal to the sum of work and heat. So I like to imagine work on the microscopic level as moving the particles of a system in a coordinated way. Heat causes random motions of particles in random directions, and this distinction between random and non-random motion helps us see how delta U must be equal to the sum of heat and work. Energy changes must either involve random or non-random motions. Heat is defined as the transfer of energy through random thermal motions, and contrast this with work, which involves energy transfer through coordinated motions. We typically observe heat transfer as a change in temperature, although we will see that a change in temperature is not essential for heat transfer. For a particular system undergoing a particular process, remember heat is path dependent, the coefficient that relates heat to temperature change is called the heat capacity. And so in general, we can write that a change in a heat transfer Q is equal to the integral from T1 to T2 of the heat capacity dt. And the heat capacity depends on temperature, which is why the heat is path dependent. The units of heat capacity are something like joules per Kelvin, energy per temperature, and so the heat overall has units of energy, and heat is path dependent since the heat capacity depends on temperature, and the heat capacity also depends on the specific path taken through state space. But when the heat capacity is constant over the temperature range involved in the process, then we can reduce this integral into a product, and we've seen this idea before. For work, we can write heat as Q equals capital C delta T when capital C is constant over the temperature range. Heat capacity is an extensive quantity. It takes more heat to increase the temperature of a system that's more massive. But we can divide the heat capacity by mass or moles to arrive at intensive quantities. So specific heat is the heat capacity per gram, C divided by mass. And the molar heat capacity, C sub m, is the heat capacity per mole of substance. We're going to use this subscript m throughout the course to denote per mole quantities. We can also use these intensive versions of heat capacity to relate heat transfer to a temperature change. And the relevant equations are shown for you here. So for a general molar heat capacity that varies with temperature, we have to use an integral and write N, the number of moles, times the molar heat capacity, and integrate that between T1 and T2. If the molar heat capacity and number of moles are constant over the process, then we can reduce this to a product, N times C sub m times delta T. Using the specific heat on the right, little c, we can write m times c and integrate that between T1 and T2. And again, if the specific heat is constant over the temperature range involved in the process, then we can reduce this to a product, m times c times delta T. And this is sometimes referred to as Q equals MCAT, the specific heat equation where the specific heat is constant over the temperature range involved. In general, do note that all of these heat capacities are path dependent, since heat is path dependent. We'll return to heat capacity in a future video and explore this dependence on path in more detail. As I mentioned, a temperature change is not necessary for heat transfer, and we can demonstrate this pretty easily using an experiment involving a phase change. Heat is involved in phase changes, so ice melting to water, for example. Ice melting to water is going to require an input of heat. However, as ice melts to water, the temperature is maintained at the freezing point at 0 degrees C. So even though we're transferring heat to the ice, no temperature change is observed. We can still calculate heat transferred another way when no temperature change is involved, and it uses this idea that internal energy change is the sum of heat and work. Energy change must involve either non-random or random motion, so we can write delta U is equal to the sum of work and heat. And so the heat can be calculated as the change in internal energy minus the work. So if we know the work and the internal energy change, we can calculate the heat. Heat is the difference between the change in internal energy and the work. This is also useful in other contexts, which we'll see in a second. Let's think about intuitions for the sign of heat. We talked about the sign of work as being related to the change in internal energy, giving more energy to a system amounted to positive work. The same idea applies to heat. When a process involves no work, the sign of heat points us directly to changes in the temperature or internal energy of the system. Positive heat is associated with an increase in temperature or internal energy. So when heat flows into a system, increasing its internal energy, Q is greater than 0. Negative heat is associated with a decrease in temperature. Heat's flowing out of the system, so the internal energy and the temperature are decreasing. These intuitions are consistent with the equation we've written down before, delta U equals W plus Q. And this idea that heat is equal to the difference between change in internal energy and work, we can also use in the context of these two ideal gas compression paths to calculate the heat. The internal energy of an ideal gas depends only on the temperature. It's not actually difficult to understand why this is so. It has to do with the fact that ideal gas particles have only kinetic energy, right? No potential energy. And so only the temperature affects the internal energy of an ideal gas. Changes in volume, as long as the temperature remains constant, don't affect the internal energy of an ideal gas. So the gas temperature remains constant throughout both processes. So the change in internal energy is 0. This means that we can write down the heats directly just as the negative of the work in each case. So Q1 for path 1, just the negative of W1, and Q2 for path 2 is the negative of W2. Note here again the usefulness of this relation, delta U equals W plus Q.